My name is Tamas, and I'm a data scientist with the Sophos AI team, and I will be talking about using LLMs for web content filtering. So obviously, you have me as the speaker, and two of my colleagues contributed to this paper, Sean Bergeron and Konstantin Berlin, who we have in the audience, who supervised the project, so thank you. In this talk, first I will briefly talk about the motivation, why we think web content filtering is important from both the security and the productivity perspective. And then I will explain the deployment environment that we have for this specific model and how we are trying to match it with our validation setup. And then finally, I will go into explaining what kind of models we tried and what were the results in terms of sample efficiency and the size of the models and a bit of model distillation at the end. So web content categorization is essentially taking a URL as an input and assigning a category to it. We believe that the security posture of an organization is partly a function of the web content their employees browse. So it's important to understand it to the best of our knowledge. So if I put my IT administrator hat on and I look at the URLs that my colleagues are looking at in their work hours, and I look and I can see update.microsoft.com, like that's perfectly fine, nothing to see there. So probably I wouldn't want to filter it either from the security aspect or from the productivity aspect. Now, if we move one bit further, there are a bit of a gray zone categories like dating sites. If someone is browsing a dating site in their work hours, like, is it good for the productivity? Maybe not, I don't know. It's up for the organization to decide. And then finally, we have the critical categories in the top right corner. So like if I'm an administrator, I'm not particularly happy about colleagues torrenting in their work hours from doing intellectual piracy. If I'm the legal department, I'm not particularly happy about colleagues buying drugs in their work hours. Or if I'm a colleague, I'm not particularly happy if someone watches porn next to me. So this is the problem that we set out to solve. Internally, we track 50 categories for this project. And that's essentially what we want to do, is to assign one of those categories to each of the URLs in our logs. Traditionally, the approach for this is without using ML is manual, meaning that we have a set of colleagues, analysts, whose job is to look at web content and manually assign categories to it. So that means that we have a finite amount of time that we want to make the best of. So we need a strategy how to utilize that time. And this is actually what we do, is that we take all the URLs from the telemetry that we have and rank order them by their domain. So the most popular domain goes the first. So imagine that would be google.com. Everyone is using Google. So I assigned the category search engine to it, and I got my telemetry covered like 20% of it. Then I move on to the next, which would be, I don't know, Facebook, and so on. I move down the list. But the thing is that we have a finite amount of time, and this is what this plot shows. So on the x-axis, we have the domain popularity on a log scale, and on the y-axis, the proportions of labels that we have. So you can see in the most 10 popular pages or most 100 popular pages, we have 100% coverage. But as we approach the long tail of the internet, we sort of ran out of time and we had no way to keep up. So that's why we need to utilize ML for this. Now the question is, how bad is this long tail issue? Oops. This is a uniformly sampled 100K URLs from our daily telemetry, broken down daily. So on the x-axis, we have days. On the y-axis, we have number of URLs looked up for that day's sample. And each bar has two colors. So the orange one is something that we had a label for from the analysts, and the dashed one is something that we are completely blind to. So it turns out if we sum up the long tail of the internet, we turn out to be blind to roughly half of the telemetry that's going through our products. So we don't know if it's an update side in the dash stuff or is it someone buying drugs. So that's what we want to solve. Now, as for the deployment scenario, this is a pseudocode for generic detection logic for AV vendors. This is not specific for URLs, but with Sophos, we have this for most artifacts that we are trying to detect. And the story goes something like this. I have a URL, which is my current observation, and it goes through this detection logic. So was this URL manually labeled by an analyst? If it was, then it goes through. Maybe it was a trusted update site. Did it violate some kind of a policy? Maybe it was a TLD that we don't like. If it did not, it goes through the next one. Was it in a blacklist? Is it a I don't know, malware site? If that goes through as well, then it goes to detection rules based on manual labels that I will explain in the next slide. But the key thing to see here is if none of these policies or rules hit, then and only then the ML model is utilized. So for most AV companies, I believe the ML models are not really deployed in a standalone mode. So they have to be evaluated jointly with the policies where they are deployed. So this would be a labeling strategy for URLs. So let's say I have a URL that is onlineshopping.com. I assign a label to it. This is a shopping site. One labeling rule would, or strategy, or detection rule, or signature, whatever you would want to call it, would be like everything from this domain is a shopping site. Or you can go more sophisticated. Everything from this domain that does not have the word gun in it, the shopping site. So you get the idea. So you are trying to do label propagation from domains. And the reason that I keep bringing this up is sort of captured in this table. Has 4 columns. In the first one is where we have our training data. So those are the domains or URLs that we have labels for. So as you would imagine from our labeling strategy, you have Google, Microsoft, and variations of URLs in it. Now, on the rightmost side, you have the unlabeled data, which is what we want to essentially label at the end of the day. And in the second column is I believe is the industry standard that we have currently, which goes, which is called at least in our group a time split. The way it works, we pick a timestamp, and everything before that timestamp goes into the training data, and everything after that goes into the test data. And this says I have never seen this URL, this specific URL, but it also means that I have seen something very much like it before. So it becomes a near duplicate detection problem, which is something that the detection rules probably already take care of. So to mimic the deployment environment, we constructed this domain and time split set, where we also pick a timestamp before everything goes into the training set, but we are not allowing domain repetition in the test set. So essentially, we are trying to construct a harder test set that tests more of the generalization capability rather than just the peer duplication issue, right? And if you look at it, it's those two distributions with the unlabeled data. Those are more alike. So a bit more specific things about the data. We sampled 10 million URLs from our telemetry, from half a year of data. We constructed the validation set from August to December, both validation sets, both test sets. So the time split was constructed based on the first in time of the URL, and the domain and time split was constructed on the first in time of the domain. And as you can see, since this is a manual process, there aren't that many samples in the unique samples in the domains. Right. So on this slide, we have the results for this data. In the table, we have 5 rows. Those are the 5 candidate models that we do at the problem. So we have Expose, which is a model architecture that we had for a very long time. It's a one-day convolutional model. that we tried to beat. BERT Tiny, which was at the time was the smallest distilled version of BERT. Then we also tried BERT, which is the choice by Microsoft to do URL categorization. And then we tried T5 large. I think at the time that was the largest model that we could fit in a single GPU. And then GPT-3 because why not? So takeaway one, LLMs are good at web content filtering. Takeaway two, we have the two bits side by side. So on the time split, we can see that pretty much every model is doing almost perfectly. These are results in terms of accuracy. And there was really no way of telling them apart. And on the time and domain split, we get 64% accuracy, which is not spectacular. But then again, this is a harder problem to solve. And also we could see differences in model performances. So we were able to pick out the best one. Yeah, so and takeaway three, LLMs are huge. So that was the next question. Do we really need to deploy GPT-4 inline to do web content filtering? And we really hope not. So the next thing we did is called model distillation. We are doing a really simple version of it. So we have the label telemetry data that the analysts label for us. And for model distillation, you will need two models. One is the student model and the other one is the teacher model. So for the teacher model, we picked T5 because that happened to be best at the 10,000-ish sample region. And we fine-tuned all weights of a T5 large. And that concluded our teacher training. And then we took the unlabeled part of our telemetry and we scored everything in the unlabeled part of the telemetry with the teacher model. And the next simple thing that we did is that we mixed these two data sets together. And that was the input for our student model candidates, which was the conv model, the BERT Tiny, and the BERT. And we fine-tuned those and looked at the results. Yeah, so we have the results from the previous slide. One thing to see is that the x-axis there is the number of training samples. So going from 10-ish training samples to 1 million. So the LLMs are pretty happy with 10,000-ish data, and they reach the peak performance there. And the next thing we wanted to see, what happens if we throw more data at it? So on the right plot, we have 10 million training samples for each data point. The one thing to see there is that the x-axis is a LLM sample ratio mix. 0.0 means that we haven't used LLM labels there yet. So we just end up by one magnitude the number of training samples, which meant that all three student models started to perform better, but still nowhere near as the teacher models. So the red dashed line is the best performing student model before distillation, and the green line is the best performing teacher. So essentially the goal is to move the red dashed line, the top one. So what we did next is try to add various try to add the LLM labels at various ratios. And one interesting thing to see is that at 0.1 ratio, where we are not even using our true labels, all three of the student models perform on par with the teacher model. So on this particular data set, URL term, so Microsoft choice was the best model. So again, that's a BERT-based model. So it got 47% accuracy on the domain split and 99 on the time split. But it's a 110 million parameter count model. So look at the column one before the last. Those are the parameter counts relative to the teacher, which is pretty good news because even for 14%, we beat the LLM that we set out to do. And even for below 1%, we can get ballpark the same performance as with the LLM. And these are pretty small models, so just only question of an SLA, which one we want to deploy. Yeah. So 74% is still not that great. So we looked at the results, what's going on there. These models are actually pretty good. So one failure motive of this model is coming from our experiment setup, which is that we are doing one URL, one label, and that does not necessarily reflect the reality. So the first URL was categorized as health and medicine, whereas the analyst gave it the business. Both are true at the same time. Also, the inverse is true, where the online wine shop was categorized as shopping by the LLM. The analyst gave it the alcohol label. So this is one set of issues that can happen. The second one is when there is a misleading keyword in the URL that was payforthegas.com, which was categorized as religion. Apparently, it's a gaming site. And then finally, where this model is not going to help anyone, where the URLs cannot be considered as semi-sentences, so they don't have intelligible words in them. So yeah, there we have just no chance for that. So yeah, as to conclude, LLMs are great for web content filtering. Luckily, you don't need to deploy them. You can use LLMs to get pretty good at the task just for a few training samples. And then you can distill that big LLM into smaller versions of other models. And also try to introduce more rigorous signature-based bit instead of just the standard times. Thank you.
Okay, I think we have time for a few questions.
Doing this classification, is it just on the domain name? Do you include query parameters? What else from the URL is included?
It was an ongoing process. For now, we include the path, not the query. Yeah, I think a fragment is stripped too. The protocol is stripped too.
And just a follow up on that. So this is only operating on the URL strings you're observing. You're not pulling any context from like crawling the page.
Yeah. So this thing is operating as a pre-filter for more expensive models that pull HTML or image. So yeah, we needed this because this is very lightweight, so we can do it on large scale.
We have a couple of questions in the chat. So how do you manage the risk that you misclassify fraudulent domains into a benign category, such as adobelogin.com?
This is primarily for categorizing URLs into one of 50 categories, which have, that's not a binary, is it malicious or not? So the reason this worked, I hope well, because these categories are trying to advertise themselves within the domain. So this is absolutely vulnerable to adversarial samples.
Another question in the chat is, did you ever run into domains that spoofed legit domains, and how did the LLM respond?
Sorry, what domains?
Did you ever run into domains that spoofed legit domains, legitimate domains?
Yeah, I think it's the same answer to the previous one. So these are mostly advertising sites that we are trying to capture here, not adversarial sites, because that would be adversarial for humans too. Like,
other questions?
Is this a multi-label classification task, or you just predict a single label?
Single label. So in reality, it should be multi-label, but the data limitation is the label.
Any other questions? Okay, if there's no other questions, let's give our speaker a round of applause.